Hello, welcome back to our lecture series on power generation, operation, and control. This is lecture 7B. It's the second half of the lectures on economic dispatch of thermal units. And if you remember, we introduced this function f of p up here, which is the cost function, of course, and it's dollars. Okay, remember that, dollars per hour. It's how fast you're putting your costs or your dollars are being eaten up to generate power. How fast are you putting money into the plant to get power out? And so this is the cost. Okay, it's really cost rate. Same thing over here. And if we had a linear cost rate, in other words, we have a straight line like that, then the incremental, the derivative, is just a flat function like that. If we had three segments, okay, we had a straight line here, a straight line with a little higher value, and a really straight line like this, well, then we get three straight lines here. Three flat functions in here. These two functions are very useful for doing the economic dispatch and doing the costing calculations quickly, because especially if you think about let's take the one over here. If you're looking at these functions and you have a number of generators and they all have just a single linear cost function or a single number for the incremental cost, well, then you just rank them lowest to highest and start adding up power until you reach your total generation. Now, if there's any, this says that the units will come on from the minimum, then they go up to the maximum, then the next unit, then the next unit, and so it's very easy to just build a table that you look up and tells you what units are generating what very, very fast. You don't have to do any lambda search or anything like that. Okay, so we're going to talk now about using linear programming. You remember we introduced that in the general build up to this chapter as a method of solving problems. And we'll find out later, especially in optimal power flow, but in the course here, if we have three linear segments, okay, we've got this nonlinear curving function down here, and we made three segments out of it. Well, with three segments, we can actually set up this problem as a linear program to do the economic dispatch. So we start out and we say that the total cost is the minimum cost. Now let me come back to this. That's the cost right here. Whoop, I'm sorry. That's the cost right here at the minimum. Now, then I add a slope 1, S is the slope times for the first segment times the P gen for the first one. And then if we assume that the P gen is always between 0 and some max, if the slopes are in order S1, 2, 3, then when the first segment is being used, the P gen for the second and the third segment will be 0. But once you hit the max for the first segment, if you want any more power, then this number has to start coming up from 0 up to its max, and then this one. So it loads in this order, first, second, third. But you'll notice that this function across the top is all linear. Okay, it's a linear function. It's got a slope times a variable, a slope times a variable, and so forth, plus a constant. So it's a linear function. These are just inequality constraints, very easily handled by linear programming. Last of all, we say the total generation is for any particular generator is simply the sum of the three generator segments at the generator plus the minimum. I want you to look at this S1 for any particular value, and that of course is the slope, and you take the difference for the P gens and the difference for the F, and you divide the difference of the F numbers, the cost rate divided by the P, and you get the slope. So there's the formula for the slopes. And so now we want to minimize over all the generators for these three. Let's say each generator in this case had 3 segments to it. Each generator segment has a set of limits, and then we have the final for PI. And last of all, lest we forget, we have the PI equals P load. This is our final loading constraint for the problem. We do not build a Lagrange equation for this. It's done with linear programming. Here's the top one is the cost. This is the cost, and this is a set of inequalities. That's just the range of the variables. And then there's a set of equality constraints that tells you how much each PI is as a function of each segment generation. And then there's the overall. This is all the sum of the PIs equals the P load. Now, example 3A in the book is solved with a linear program. And what I did was I said, okay, if I have one segment right here, each generator has a single segment. Notice that then it's going to have it's going to come out on this one will be at its min. These two are at their max. It's 850 megawatts. That's very unrealistic for this case, although it's an approximation. It's not too far off. Then we go to 2 segments, and it changes by quite a bit. We go to 3 segments. We get up to 10 segments, and we're at 385. Now here's the answer down here. In the bottom rows we have the answer. So this is the final answer: 393, 334, 122. Well, 10 segments were not too bad. 385, 340, 125. If we go to 50 segments, the LP can solve this to 393, 335, and 122, and it's only off in the total cost way out here in the 3rd decimal place. So we can get a very accurate economic dispatch. Now the nice thing about this is that if I do it with LP, I can add other kinds of constraints. And we'll see later on that I can add constraints having to do with the transmission system or anything else I want into the mix of constraints in the LP, and it'll give me a dispatch that meets those other constraints too. Okay, here's another application, what we call using dynamic programming. Here's the P, and I have 3 generators, 1, 2, and 3. And rather than just look at numbers here, but let's assume that in the beginning we get numbers if we plot them. So here's the plot for the first generator. There's its cost function, and there is its incremental cost. The incremental cost, starts out high during this, and then it's low, and then it's high again. So it goes down, up, and over. The point of this exercise is to note that you cannot use lambda search. You can't simply put a value of lambda in here and solve, because you don't know which is the intersection, which one counts, and so you can't use lambda search for this particular unit. Similarly here, the cost comes down and goes back up again. Here the cost stays the same, and it just comes down gradually and goes up. So these are all examples of non-monotonically increasing functions, and you can't use this to solve an economic dispatch with lambda search. Well, what we do is we go back to that allocation method that we presented, where we say, okay, I'm going to invent something called F2, which is F1 of D minus P2 plus F2 of P2. So we're going to say, okay, I will decide what P2 is, and that's across the top here, and then I will decide what D is, and then we can take different combinations of the D and the P2. So if P2 were let's say 75, let's see, there's 1, 2, 3, 4, 5, 6 columns here. They don't exactly line up with this particular graph, but if I take the final column here, and I say P2 is 150, well then there's the F2 value. If P2 is 150, then I can set D for 100. Well, I can't, I could have this value over here for P2, and then I know what the value for, if D is the delivered power and this one is 100, then the function actually comes in down here. It says, well, pardon me, for 200, then 150 would be the value for D minus P2, and so I can get values in this table, and that's the F2 way over here. The important thing here is that we get this column. We get this column right here. I'm going to draw down the edge of it. That's the numbers that I want versus P2. So there's F2 of P2. I generated that with this table. Then I do a similar thing here with F3 as being F2, which I just generated, D minus P3 plus F3 of P3. So here's P3, and I draw examples down here. Now I only really want a D. I want it for 310 in this problem, and so I'm just gonna generate these two numbers over here, and there's the F3 and there's the P3. So I have that developed, and then I know the cost, and so now I can work my way back and say what the output of these should be. So now if I interpolate, I would end up saying that, well, this one will stay at 150, this one will stay at 50. Now if I'm only going to do 310, then the interpolation here is P2 is 110, and there's a cost. So I can actually use this to dispatch the three generators economically without using a lambda search. There's no such concept of matching lambda. Let me back up again and say this kind of thing, especially where you have an incremental cost function whose value goes down and then back up and then down and back up, or something like this. When this is the incremental cost function, you might have an intersection here, you might have one here. You can't use a lambda method. There's one other drawback to this thing, and that is the fact that if I have a number of these generators and the load goes up slightly, you really want the generators that are there to go up or stay constant. But with this kind of a dispatch, it may turn out that the next value of dispatch, some of the generators will go up, some will go down, and they may go up and down by large amounts, which makes it an impossibility to actually use these non-monotonic functions in a real, especially for operations. If you want to put an exact, precise valve point function in and find out what the absolute minimum cost would be, you can do it with this method or with any number of very exotic methods that have been published in recent years. However, you can't operate the system that way. And that's why most power companies do not use those kind of functions in their operations. Okay, here's another topic. Suppose we had a set of generators over here, 1 through n, and I don't want to run an economic dispatch. Every time I want to solve something to do with this system, I don't want to do n generators here against this t generator. This is a plant that's got some special issues. Let's say fuel scheduling. I'm worried about its fuel. What I really would like is something much simpler. I would like a 2-generator thing. And this S unit here is what's called the composite. S is going to represent all of these generators. And to generate a composite cost function, we say, all right, the F for this function here, the F of S, okay, F of S, is the sum of all the other generators, 1 to n, where P sub S is the sum of the outputs. So that we add the cost up and we add the megawatts up. And we're going to force economic dispatch conditions to exist, and that is that they all are at the same lambda. So to do that, I run a program as follows. I calculate the minimum that lambda could be, and that's the minimum over all the generators. And then I calculate the maximum as the maximum over all the generators. And then I start it, and I say, okay, set lambda to lambda min right here. Calculate the P such that the df/dp equals lambda, and I do that for all the generators. And now I add the P up, and I say that's PS, and I've got this superscript alpha. So I say, okay, I now have the total output, and I will calculate the total cost, and then I increment lambda right here. I just increment it by delta lambda, and unless I'm up to this maximum, I go back and I do this dispatch again. So I keep calculating points like this. So here's my 3 units, and I calculate a point here. Then I increment lambda, and I calculate a point here and a point here all the way up to the top. So I keep incrementing lambda and getting points. So this is a point. This is the total cost versus the P output. Well, there's a well-known branch of statistics and mathematics that says it's possible to take some points like this and using a curve, what are called curve fitting techniques, to come up with a function. In this case, we'd like to have a quadratic function that represents these points. So we used a curve fitting technique, least squares curve fitting, and we got this quadratic function down here in P sub S, and it goes all the way from 300 to 1200 because it's got 3 generators, so it's covering that. But that's the S. The PS can go all the way from 300 to 1200, and there's the composite generating curve. Now I can just use this with another unit for a study, and I have a very fast dispatch that way. Here's another problem that you find in running the power system, and that is when the power system experiences an increase or decrease in load, we want to tell our automatic generation control. There's a program or a function in the control computers that says we have to raise generation. If the load went up, we have to raise load. If we don't, then there's more load than generation. We're going to have the frequency's going to start to go down. In order to keep the frequency more or less constant, we're going to raise the load on each generator, raise the generator output when the load goes up. Similarly, we do that for the downward. So if the load drops, we have to reduce each generator. And we do this allocation by predicting the change in each generator output with a small change in lambda for each generator. So here's the idea. We have the load here, and the load just went up. Okay, it went up like that. And you'll notice that each generator went up a little bit. Each generator went up a little bit. So here's the delta in this generator. This one went up by quite a bit, and this one went up. And what we're saying is that the amount of increase, the amount of each of these up arrows here for the 3 generators should match this, should match the increase in load. So the generators are all going to come up because the load went up. Now, if it was going down, then everything would go down. Oh, if the load dropped down, then the generators would go down. So but what we need to know is, how much is this? How much is that? How much does this one get? We didn't just take the load increase and allocate it 1/3, 1/3, 1/3. What we would like is to somehow do this in an economic way. Well, here's the idea. If I have an incremental cost function here, df/dp, and I increment lambda, then how much of an increment do I get to the delta p? That's what we're going to do. And what we do here is we say, well, if that's all you want, if I can get the second derivative, and there's delta p across the bottom here, and here's delta f. This is the change in f prime, the change in the first derivative. Well, then I can say, well, what is the slope of this? Well, it's the slope of the incremental is the second derivative. And so given a delta lambda and the second derivative here, I can calculate the delta p. That's the way we're going to go about it. Is we're going to say if I take a change in lambda and I know that the second derivative for this function, then I can calculate the delta p. And what we want is we want the PD, or the delivered power, which is load plus losses. We want that to equal the change, or the delta P, on all the generators. That's all it says. It says each generator is going to add a little bit, and that equals the change in demand. Well, if I do that, then I can say each of these is equal to delta lambda times 1 over f. So I solve it. You can see this down here. I solve each delta P as a function, as saying delta lambda over f double prime, the second derivative. So here's the sum, 1 over f double prime times delta lambda. Now what I want to do is I want to calculate my participation factor. My participation factor says, what is the change in generator I divided by the total change in load that I need to track? And so if I'm doing that, if you substitute now remember here I've got the delta PD as delta lambda times this sum. But what do I put in for the delta lambda? I go back up here for delta PI. So I take the 1 over f double prime for the I generator, and then I take the sum, and that's this participation factor. And then what we do is we say, if I know the participation factor for a particular generator, and again, the participation factor is this 1 over f double prime divided by the sum of all the 1 over f double primes multiplied by delta PD. So that is what we call PF, or participation factor. So once I have this number, I just multiply it by the change in PD, and I know how much delta PI to put in on a generator. And that's what we tell the AGC. The AGC actually uses this participation factor so that it knows how much to change. Now, it's an approximation. We're linearizing around a point here, and it's not good for too far a change across the range of the output of the generator. But every time you do the economic dispatch, you'll update the so-called base point and participation factor. By the way, the base point is just the economic dispatch. So we have an economic dispatch, and now we have a way of going up and down around it. So if I draw that on a graph, I say, well, here's unit number 1, and this is the megawatt, and then I have a slope. And this is number 1 here, and then here's number 2 as a different megawatt, and maybe it has a much steeper one. It's going to participate a lot more radically than going up and down than number 2. And so I have these are the base points, and the participation factor says how much do I change. If I had one like this, it would say it's flat. It would say no matter what happens, that unit doesn't change. Okay, when this one will take a lot of change as the load changes, and that's how you control. So we'll see this come up later on in the AGC discussion. Another topic we're going to start now, and then we're going to finish it up later when we talk about transmission systems. Obviously, these generators don't all connect to a single bus with a single load hanging on the bus. They go through a transmission system. We raise the voltage, it goes through transmission lines, substations, gets lowered to sub-transmission and distribution voltages to thousands and tens of thousands of loads out there at the same time. At the same time, and I'm going to draw a wavy line here. We heat the air. We heat the air with the lines, especially on a hot day when the load is heavy and there's no wind. We get a loss. We get losses. Let's say 3 to 5% for a transmission system, not counting the distribution system and other losses, just the transmission system. So it's a lot of energy, and so it's going to pay us to start doing our economic dispatch, where the equality constraint now says load plus loss minus the sum of the generation equals 0. So our economic dispatch Lagrange function f of t is still the sum of the operating costs of the generators, lambda times phi, but phi now has this function down here. So here we can write this. I'm sorry. This is phi right here. Okay, so accept that as my overprint there of phi, and so phi is this function right there. So when I take derivative with respect to pi, I get a derivative of this. I get a 1 or a minus 1 really, and then here I get what's called the incremental loss, dp loss dpi. Now, because I put this minus sign here, I like to put the minus sign out in front, so I have minus lambda times 1 minus the incremental loss, and that just makes things come out in the right order. Or we can say that this is the equation. Now remember, economic dispatch originally said df dp for each generator equaled lambda. But now we've got this extra term in here. This extra term, and that means that we're going to have to solve. It's a little more difficult to solve. We'll see later that the incremental losses and indeed the actual loss itself is done with a power flow program. We calculate the incremental losses and the losses on the network with a power flow program. The way to do it is you assume this is fixed, you assume that these are fixed after you've calculated them. Well, if they're fixed, then I can just do a standard economic dispatch, and after I do the dispatch, I have new PI values. I go back, I solve the power flow, I get new loss, new incremental losses, and I iterate back and forth. We will show this in great detail and the effect that the losses have when we do at the end of the chapter on transmission systems. Okay, one more topic for this chapter, and the very, very important one is the concept of locational marginal price. Let's say that we have a power system here. I have a generator number 1, and that generator is willing to sell 400 megawatts at $5 per megawatt hour. It's willing to sell 800 megawatts at $7.5 per megawatt hour. Generator 2 will sell 200 megawatts at $6.50 and 400 at $8. Now, if I plot these, and let's go back here. I'm sorry. This generator can put out 1,200 megawatts. This one can put out 600. So I have 1,800 megawatts I only have 500 here and 4. I have plenty of generation. And we'll assume for the time being that there's no limit to the flow on this line back and forth. Here are the generator cost functions, dollars per hour, and it's 5 and 750. It's 6 and 8. Now, the base dispatch, how do we do it? Well, we start out with the lowest priced energy. That's that $5 one. And let's just say we take 400 megawatts and we put it in here. Okay? Now, we've used up, remember I have the $5 energy. The next in price is the 650, which comes from this guy. And so I'm going to take 200, and let's say I take 200 and put it in here. So this is 400, and I put 200 in here. Well, now what? Now I have to go to the next most expensive, and from here I can take 700. I need 300 more. That's 400, and 200 is 6. I need 300. So I take another 200 from here at 750, and then I take I take 100 here, 100, and then I take 200 and I go around this way. 200 goes through the transmission line. There we go. So I'm supplying 500 here, and I'm supplying 200 here from this generator and 200 here, so I'm meeting the 400, I am meeting the 500. Now suppose I come back to this bus, and this is the concept here, and I want to add 1 megawatt to this load. 1 megawatt. If I do, I'll buy it at 750 because there's still energy left. I can go up to let's see, let's go back here again. I can go up to 800, and I'm only using 100 out of there. So I can buy the next megawatt from this generator and supply it into the load right there. Or suppose I now want, and so we say that the cost of the next megawatt is 7.50. Suppose over here I want to go 1 megawatt, and it turns out that I can go back to the same place here, and I can let me make this dotted, and there is 1 megawatt from the same generator at 750. So I supplied that extra megawatt at 7.50 over here. So LMP at both buses is 7.5. 7.5. No matter where I am in the system, if I put 1 more megawatt on, I pay 7.5 because I'm buying it from this generator. Now, if we limit the flow here to 100 megawatts, that's the key to this. Well, I will get 400 over here at the price of 5. I will get the 200 over here at the price of 650. Then I'll come back here and I'll say, let's see, I've got 400, so I can put 100 in here. So this is 100, and this is 4. Remember that. Now I've done this one. I've satisfied him, and I bought the 100 from this 750. And now I'll take another. I'll take another 100, and I'll say, well, okay, we've already got 200 into this load from this generator. I'm going to put only 100. Oh, I can't get any more. So there's 100. And this guy now has 200 plus 100 is 300. He has to come back and he has to purchase the last 100 at 8. So I've got this one coming in here at 100 too, but he's at 8. So the last megawatt here, or if I were to add 1 megawatt, it would be 7.5. Here, the last megawatt plus 1 would be 8. So the LMP at bus 1 is 7.5, the LMP at 2 is 8. The LMP is different because we say this is transmission limitation or congestion in the transmission. You can't get the power through the transmission system, so this one has a higher incremental cost than this one. That's the difference. This is a higher incremental cost than this one because of the congestion. And power is always flowing from the lowest LMP bus to the higher cost LMP bus. Okay, let's just do a little summary. Economic dispatch is performed at even time intervals, or upon a significant load change in real time when we're studying. So it's very important as you're operating the system to keep doing economic dispatch to keep the system operating at the lowest cost. If you're doing a planning study where you're looking at, let's say, adding a new generator, you're going to do an economic dispatch with the new generator to see what the total cost is going to be. Or if you're putting a new transmission line in, then you do an economic dispatch to see how the system performs. So the economic dispatch is a very basic module, very basic part. That's the operating cost of the power system. Power companies pay a lot of capital costs to build plants, to build transmission, and then they pay huge amounts for fuel costs and to keep their generators, to run their generators. Of course, there's maintenance costs, personnel costs, and so forth and so on, but a big part of it is fuel cost, and that's the economic dispatch, is to determine what that number should be. Thank you very much. We hope to see you here soon when we get into our next chapter in this course.